Hi, welcome back to PR Tech Talk. Today we're going to look into the DAC, the digital to analog converter. In the previous two videos we looked into the analog to digital converter, which is the more common one. And that is when you have to have some signals into the microcontroller. But sometimes you also want to drive some signals out of the microcontroller and need that to be an analog voltage. And that is what we're doing today in this DAC. So we start up as we normally do with creating a new STM32 project. And my lab will be on the STM32 Nucleo board, and that will be on the G071. But you can do with any microcontroller that you have on your board that you have. And we select the Nucleo G071 RB or whatever board that you have. You are free to call it whatever you want. I call it G071 DAC. And I initialize all peripherals to their initial mode. I can also start by saying that I'm running on Cube IDE 1.14.1, which is the currently latest version. Now let's see, 1.14.1, yeah. And I also updated the J-Link interface on my Nucleo board. So here we have the board, and what we're going to do in this time, we're starting with to take a look in the sys file and make sure that we have the serial wire there, so we can make debug. We go to the RCC, and as normally I try to use the internal clock as much as possible, just to minimize the need of external clocks. And so we will use the high-speed internal clock, and that is on 16 MHz. But I will run the board on its maximum possibility, and that is 64 MHz, stands there in blue, light blue. So I just write 64 here and hit enter. And it says, with the current solution, you can't find any solution, but do you want me to do whatever I can to make it to 64? And I say yes. And what it does, it changes this multiplexer here from the high-speed internal, which was the clock source from the very beginning, and now changes to the PLL clock, and there we have the high-speed internal going into this multiplexer, and with this divider and multiplier, we get out 64 MHz. And we also need to take into consideration that it also puts out this 64 MHz to the APB timer, and that is something that we need to have in mind. We get back to the pin and configuration, and my lab today will be on DAC. And you can use DAC for many things, but in this case I'm going to do a bit more elaborated demo. I will use it like a timer triggered DAC, and I will also have DMA. So in the start I will start making a sequence or a series of analog values with a small routine I have, and I can then change it from different number of positions, and I will also take a look and see what that has for you will see later on, so stay along, you will find out. And I will also then have the DMA and the timer to trigger the DAC to output these voltages. So when we hit activate, we can get to this prescaler, and here we write 64 minus 1. This divides then the 64 APB clock with 64, and we will get 1 MHz. And then we have the ARR counter. It stands here for counter period, auto reload register, and we put that to 10 minus 1. We then have it will count up to 10, and if we have 1 MHz in, and that means effectively that we will get 100 kilohertz out of this timer. So I will trigger the DAC 100,000 times per second, so with 100 kilohertz. So what this then do, it will trigger the DMA to read in the next value and put that to the DAC, and the DAC then outputs that value. So we will take a look into that. But this is what we need to do here, and we can then move on to the analog section. And in the analog section, we are going to take a look in the DAC. Here we have out 1 connected to, and we will have only external pin. And if we take a look in the DAC one, it will go out to, we see here the PA. We have the DAC one out, so that is on signal PA4. So if we just remove this one again, you will see that this one is then taken away. So we have it on, and you will have it on DAC1 output on PA4. And we will have it on normal mode. We will enable the buffer, so there is an output buffer driving the output pin. And the trigger. Now this is interesting, because now we will need to see what will trigger this. And I said that I would like to have the timer to trigger it. And I said that the timer 7 trigger out event. And what we can go back, what I think I missed in the timer 7. We go back to the timer 7. And first of all, so see here, trigger output. So when this have divided by 64 and it gets 1 megahertz and it counts up to 10, that means every 100 kilohertz there will be time out on this timer. So we will then do something, we will update an event. So we will take a notification to an event that something happened, and then it will start over again. So this event will be triggered 100 times per second. And this event will the DAC be looking into. So we will look into the trigger 7 out event. And what we also need to do is to have a DMA. And we add a DMA and we act as a DAC1 channel 1. So remember, this is a channel 1. We had the out 1 and out 2, but we only have the out 1. So channel 1. And memory to peripheral. And so that is direction. So it will take information from the memory and put it into the peripheral. And the peripheral in this case is the DAC. And we will have a circular request. So when we come to the end in one circle, we start from the very beginning and we just go as a circle. And we will use a full word in this case. If we take a look into the NVIC settings, we need to make sure that the DMA channel 1 interrupt is enabled, and it is that as soon as you enable the DMA. But that is what we need to do here. So we can create the project for us. And as normal, as I used to, if you have seen any one of my videos prior, I just try to build the project first to see that there is no errors or warnings. But that is not expected either. So here you have the 2 tabs, the IOC file. If you hit that one, you come back to the CubeMX if you need to make any changes to the project you made. And you have the main there. So we can take a look what we have done so far. We have some private variables that is created. That is for the handler for the DAC1. And we also have a handler for the DMA. And we have a handler for the timer 7. And we also have a UART, which we won't use in this case. So we can just either go back and disable the UART if you like that, or just leave it. It doesn't make any sense or make any changes. And then we come to the private functions, prototypes. So there are some routines further down in this main C, and here is the prototypes for them. And then we come to the main section, and we start with initialization of the HAL. We set up the clocks, we set up the time, the GPIOs, we set up the DMA. And just if you haven't updated your Cube IDE to this latest version, just make sure that the DMA is prior to you starting the DAC or the timer. In a previous version, I realized that the DMA was initialized afterwards, and then it was not working as good. But that is changed since a couple of versions back. But if you're running on a late or an early version, my recommendation is to update it. Then you get all the bugs fixes. So here you have all the initializations. You have the USOTs, which we don't use. And you have the DAC and you have the timer 7. And then we come down to our while one loop, which we actually won't do anything at all in this case. And then later on, we have all these initialization files that we had the prototypes for. They are coming down here. But we won't do anything in these either. What we can do is take just a look in the timer 7. You remember that we said there was a prescale on 64-1. You have it here. So you can change it here. If you change it here and you recompile your code, or if you go to CubeMX, it will change it back. So it's not recommended to do it. You can, but it's not recommended. And you also have the ARR register. The auto reload register is 10-1. So you get 100 kilohertz out. And you also have the output here that it's trigger and an update there. So. And the USOT and so forth. But we won't do anything in this, but we need to enter some code. First of all, we need to have an include file, and we will include the math.h. And the reason for this is that we will use a function called sin to create the values for the sinus structure that we are going to put out. So that is the reason for having this library in this code. Then we need also to have some variables for us, or some defines actually. And we go down here to the user code begin private defines. And we define first of all the number pi and give it some values there, 3.14 and some digits more. And we also define something called max samples to 10. That is to make it easier to change in the code and make some elaborations on it. And we also have two values here, resolution 8-bit and 12-bit. Reason for me to do this is that the DAC have two modes you can use it on. You can use it on 8-bit, you can use it on 12-bit. And we will take a look on both and see if we can make any difference on those. So that is I'm making these res 8-bit or res 12-bit. Then we go down to user code, begin private variables. So here is the user code begin private variables. So I need to, I said I will create a series of values and put it into this. And this is where the DMA will pick. So we'll pick the first number in this array. And here we see max samples. And that is the reason we put this max samples up here. So in this case, as we have 10 here, we will just make 10 samples for the sinus wave. So it will be very granular. And the reason for me to making this is that we can see it easily. We can't see it if there is 256 or anything else. But so that we can change easily. So I will make an 32-bit sine wave val, and I will make room for then 10 positions here. Then I will make this small routine for creating and populate the sine val max samples with some values. So instead of making using Excel and taking all these values to make a sine wave for you, you can use this routine. And it says get sine val, and then it uses also this max samples as we had before, and there again. So that is the reason we use this max samples. We change it on one place and then it will affect everywhere. So it will create the sine value and put it into the I. So from the very beginning it's 0, so it will put it in sine val position 0. It will put its first value. And then when it's done, it will come back into this for loop again, and I will increment. So the next number, it will be position 1. So then it will put this value in position 1, and then it compares to the max samples and so forth. So you will have 10 samples in altogether in sign val, and we will also take a look into this. And then I also have here the resolution 12-bit, and 12-bit then equals to, in this case, 4096. So if we want to change it to another resolution, we can just change it to res 8-bit. So that is the meaning for having these macros here. So this one will be called once in the very beginning, and then we have the values and we won't change it. Then we will get down to after all initializations are done. There we have a user section called user code begin 2. So here we can actually put some code into. So what we do now is trigger this function to create the sign val for us. So we call this function get sign val once, and then we will run this code. And once it's done, it comes back here and take the next. So then we are done with that. We won't do it anymore. So while you have done this get sign val, and that one has populated these values, we need to start a timer. And we use this one, and then we need to have the timer, which timer we would like to start, and we will start at timer 7. So now the timer base 7 is started and running, and then we need to start the DAC. And if we write HAL DAC start and control space, it will get this autocomplete window. You will have HAL start, and you will have HAL start DMA. And we will use the DMA, so we will take that one. And then it asks for a couple of functions here. So first of all, it asks for which ADCL or DAC channel, so we select that one. And then we need to also select which channel. And we remember we had the channel 1. And then we need to have the data. What data should we output to the DAC? And that was this sign val. So we take this one. And just put it there. So the sign val is what we need to do. And then again, length, that means how many samples should we do. And then we use this max samples. So we have the max samples. And then alignment. If we take a look into this, we can see that the data register in single DAC channel mode. We have 3 versions. I said that you can make 8-bit and 12-bit. And in this case, we are using the 12-bit we selected. We used so the 12-bit, we can then have the left aligned or right aligned. So we write DAC align, and we control space, and then we get all these possibilities. You have a DAC align 12-bit left and right, and we would like to have that right. So there is our function. Now we try to compile this. Great, no errors. We like that. And we go with the debug icon. And as normal, if you have seen my videos before, I would like to always have the ST-Link and scan for the serial number, so I make sure that there is it detects my board. And we write OK, and it will then change. If we look up here in the right, it will change to this debug settings instead. So now it's highlighted that there is the debug, and it changed all the views. So it have downloaded a code to the microcontroller, and we will now do something. We will push this live expression, and there are some old stuff which I can just remove the old stuff by hitting those double X's, and we will add a new one. And we will have this sine val that we will take a look into. So we see sine val, and if we expand it, we can see that there are now 10 positions. And why are there 10 positions? Because we defined max samples to be 10. And we said that when we created this variable sine val, we should use it by 10. So if we just hover the mouse over this macro, it says it's 10. So that is the reason for we having 10 values here. But they are also 0, and we can now then just jump in the code. So we hit the first one, and initialization is done, and we get to this point, get sine val. So take a look, there is 0 here, and now that when we do this, we get values. So this function that we had up here has done its work, so it made a sine value from on 10 positions. So this is a very crude and rough DMA, or a sine wave. And then we start the timer and we start DAC. So we can just run the code. It doesn't seem to do something, but if we take a look into the Scopy, here is my digital oscilloscope in this case, made from analog devices, and it's a multi-tool. You can see here there is oscilloscope, there's spectrum analyzer, there's network analyzer, signal generator, logic analyzer. There's a lot of tools in this application, only this, and you can have it in the screen. So for this, it's very nice. So this is the output on the Nucleo board. And if we take a look on we remember it was the PA4, so we have the PA4, and it outputs on these pins on the Nucleo board. What we can now do, we can take this marker, which we have here, we can drag it down here. So this is the curve 2. If you take a look into this curve 2, and I will change this, you can see it's changing from down here, it's 0 more or less, 42 millivolts, and up to the main, that is 3.12. And I have the VCC on 3.3 volts, so it's more or less full swing on this one. So if we take it on half like that, and we see that the sinus wave starts from, if we see that this is the virtual 0 level, we will get up and we will get down to the negative, and then we will get up to this value again. So that is a full sinus, sorry. So coming from here up to this, that is one sequence. So we remember that we had 10 steps. So we start with 0, and then the first step is 1, 2, and then you see that this step is double as wide as this. So this is actually 2 steps. So 1, 2, 3, 4, 5, 6, 7, double, 8, 9, and 10. So these are the 10 steps that makes out a full sine wave. And the reason for me to make a sine wave this crude is that we can actually see what it's doing. If we just get a sine wave out, we will do that as well. We don't see how many steps we have. So this is mainly to showcase the number of steps. And also one other thing that is very crucial. Now that we see that we have an output frequency on 10 kilohertz. If we remember, we had a 64 megahertz clock, and we put a 64/1 divider, that means 1 megahertz. And then we put the ARR value to 10, so we take the 1 megahertz and divide it by 10, that makes 100 kilohertz. So why is then 10 kilohertz here? Well, we trigger the DAC with 100 kilohertz, and for each trigger we increment the DMA in our sine val to pick a new value. So that means effectively if we have 10 steps, we take the 100 kilohertz and divide it into 10 steps. So that means that a full swing here needs to be divided by 10 again. That is the reason we get 10 kilohertz. So if we break this one and get back to our code again. And now the feature or the finesse with this, if we now make samples for 100 for instance. We haven't launched the code yet, so that is the reason we see this scope is doesn't know what it's doing. What we can start with is actually take a look in the live expressions again, first of all. Now we have changed it to 100 values. If we expand this one, come on. Now we see we haven't done anything but changing the max value to 100. So now we have 100 positions here instead. So we use a lot of more memory, but we have memory enough, so that is no issue. And we can just also take a look if we now single step this one. Now we can see. So now that code did run, and we have all these numbers now that the DAC will. So you see it starts with roughly 4096 divided by 2. That is 2048. So we start with the mid section here, and we gradually go up to something like 4000. Yeah, you can't go all the way up. So 4059. 79 there, yeah, and then you go down again to 0, yeah, and then you go up again to 2000, something like that. So we now run and we take into the scope again. Now we can see that we have changed the time base. And if we take this marker again and we try to put it in somewhere halfway. Now you can understand my reason for having 10 position, because I have hard time counting this sweep that is now 100 positions. But you also understand that the number of steps is very valuable, and you would like to have as many steps to get very smooth, because now still you can see that there are small steps in this. I can maybe make this a bit thicker, but still you can see that there are some ripples here on each step. So there is actually 100 DC voltage steps. And over this one period, you have 100 steps. So if we just stop this and freeze the frame to see, we can see that we now have a 1 kilohertz frequency instead of the 10 kilohertz that we had prior. And why is that? We haven't changed anything. Well, it's the same thing that we trigger the DAC with 100 kilohertz. And for 100 kilohertz, we tell the DAC to increment the value and change the output. And one sweep here is 100 steps, so we divide the 100 kilohertz by 100 steps. That gives us 1 kilohertz, so that is what we see here in the frequency. Great, so this is now very granular and we can see it very nicely. We can also do like this. We can have it very nice. We can make it changes to 1000 just to see. Now we know what to expect. So we just changed the max samples to 1000 and we do the same thing again. We now have the sine value. Now we see that there are 1000 values there. And now it divides it up in 100 positions increments, so we can easily see it. So we just do like we did before. And now we will also create this 100 values on the sine wave value. So here we have all these values that is now very granular. So now we see a very nice and steady curve. And we don't see this granular because there is now 1000 steps on one sweep. And now we also can see, if we stop this one, now we get down to 100 Hertz. And that is the reason also because, as you know, we need to now have 1000 positions on each. So for one sweep, the DAC is triggered 1000 times to make new values. And that is the need for high-speed internal clocks. And that is why I ran it on max clock as well. So if you want to have a very fast ADC or DAC output, you need actually a very high clock speed. But can't we change the resolution then? If we change the resolution to 8-bit, then it must be very fast. That is not true. If we take a change on that, take a look at that one as well, and we use this res 8-bit. And we change this resolution to 8-bit. And we also need to change then this DAC line. We can't use that to 12-bit. We need to change that to 8-bit. Right aligned. And we now can change this one as well to maybe not 1000, we take 100. And so we will, as we did before, then we got 1 kilohertz output. So if there is any change, we will also have the 1 kilohertz output now. We wait for the debugger connection. And we just run it. If I hit the button, that means so. So we change the time base to 100 microseconds, and we can now see that if we make a stop on this one, we still see that we have 1 kilohertz as we did with the 12-bit resolution. So why is this not changing? Well, the DAC is actually, the value is driven from the same APB clock. So the timer for the DAC is run on 64 megahertz. So if it counts to 100 or to 4096, it doesn't make any change. So that is the reason it's sitting and waiting for the timer to trigger it. So and the reason for having a very fast then is how fast you can trigger the DAC. The DAC can be used to many things. You can also source that voltage internally to a comparator, and then you can also have it as an current measurement if you have if you would like to measure any current in your system, and you can set then the various trigger points. And I will maybe put that in a future videos. If you learned something, give it a thumbs up, and if you're not a subscriber yet, please do subscribe it, and you can just hit the round button beneath me here, and it's highly appreciated. And please leave some comments as well, what you would like to see in the future coming videos. So until I see you next time, stay safe.